In this transformation of analog filter to digital filter, we will be provided with the analog filter transfer function HA of S. So you may have a question, what kind of a filter? So looking at a numerical, HA of S will be, for supposing a numerical, 2 upon S plus 1 into S plus 3. Obtain, this is an analog filter, convert this into digital filter for sampling period t equal to 1, or it may be t equal 0.5, something like that. This will be given in this transformation. And we have HA of S, the transfer function of the analog filter, then which is converted to HA of T, the impulse response of analog filter. How that is done? With the help of it's an S domain. To convert that into T domain, we apply the inverse Laplace transform for that one. Alright, and from here we're gonna obtain that after sampling this one, H of n, the impulse response of the digital filter, How this is done? Subjecting T, sampling T equal to nt at equal intervals, that T, it may be anything, 1, 0.5 seconds, etc. And finally, subjecting this H of n, the impulse response of the digital filter, to Z transform of H of n will give us that H of Z, that digital filter which we are in search of. These are the steps to be followed during this impulse invariant transformation. And to obtain the inverse Laplace transform of, if we are dealing with this numerical, in order to obtain the inverse Laplace transform, we have to split that into partial fractions and speak something about that. So how this is, and how, as soon as, during this transformation we need to speak about the pole location and number of poles. Here two factors we have. The denominator of the transfer function gives us the characteristic equation which gives us the information of the poles and zero location poles. The denominator equal to 0, S plus 1 into S plus 3 equals 0, and this equal to 0, S plus 1 equal to 0, S equal to minus 1, one of the root, and this will be one of the pole. This will be P1, one of the pole, and the second factor, S plus 3 equal to 0, S equal to minus 3, and this is another pole, P2. This is the information for pole, location of poles and number of poles, 2 poles. And on the other half, to obtain that inverse Laplace transform, that procedure, this has to be, we need to get the partial fractions and something like that. So what factor is that? HA of S, which is 2 upon S plus 1 into S plus 3. This transfer function is of simple and distinct poles. The poles are not repeating. It's minus 1 and minus 3. Poles are different places and simple. It's not complex. So how do we split this this transfer function into partial fractions? Simple and distinct poles. S plus A upon S plus 1 plus B upon S plus 3. And we need to evaluate the A value, B value individually, then apply the Laplace transform conversion, that relationship we have. And guys, before this one, a prerequisite is that if you are a beginner and if you have forgot the previous derivations and all, what if we have a factor e raised to at and u of t? This factor is multiplied with u of t. It's a right-sided signal. Whatever signal when multiplied with this one, u of t, which commences from t equal to 0 to infinity, that becomes a right-hand sided signal. And in order to obtain the Laplace transform of this one, what to do? The given factor e of at is multiplied with the Laplace transform factor e raised to minus st, and this u of t says the integration is from 0 to infinity with respect to t. Alright, so now this is how one of the prerequisite to, if you have forgot, and we have infinity, so we need to take out e raised to negative as common from both the terms. E raised to s, negative has come out, so it will be minus a into t dt integral 0 to infinity. Alright, so applying the integration, we have e raised to minus of s minus a into t upon minus of s minus a with the limits 0 to infinity, and plugging in the upper and lower limits, the Laplace transform for this one, so, thinking that it's x of t and the Laplace transform this one. Alright, so which is x of s, the Laplace transform, and what do we have? Minus of s minus a, upper limit e raised to minus of s minus a, in the place of t we're gonna plug in infinity, minus e raised to minus of s minus a into 0. Anything into infinity, this entirely, this becomes this factor in the exponential minus infinity, and anything into 0, that will be, this will be entirely 0. So guys, this becomes 0, this factor becomes 0, this will be 1, and so what do we have? Minus 1 upon minus of s minus a, and this is plus, so 1 by s plus s minus a. So remember, if you have a plus over here, if you have a plus over here, this will lead us to minus, and if you have a negative over here, this will lead us to plus. Alright, so where did we start from? What I was trying to say, guys, it's a Laplace transform of e power at u of t equal to 1 upon s minus a. Now applying the inverse Laplace transform either side, this gets cancelled, and so we can say that inverse Laplace transform of 1 by s minus a, we have to write like this. Remember this one, this is very much important. We have spoken, right, ha of t, subjecting to inverse Laplace transform, ha of t, impulse response, then sampling will give us the impulse response of the digital filter h of n. During this we will come across simple pole and the inverse Laplace transform pair. So what it is, the inverse Laplace transform of 1 by s minus a is e power at u of t. Remember this factor. Why? Because we will almost all the numericals will be leading to that standard Laplace transform pairs only. And how to evaluate the a value? A value, we need to consider the transfer function again, 2 into s plus 1 into s plus 3. This transfer function is multiplied with a residue, which is s plus 1, a residue, and after cancellation, whatever s is left over, that is plugged in with minus 1. Alright, so s plus 1 here, this gets cancelled, and a is given as 2 upon s to be plugged in with minus 1, isn't it? Minus 1 plus 3, that will be 2 1 2, that will be 1. A value will be 1. And how to evaluate that b? B equals the same thing, the same transfer function, 2 upon s plus 1 into s plus 3. This transfer function is multiplied with the b residue. In the sense, it's the transfer function is multiplied with s plus 3, subjecting s equal to minus 3, this pole. Alright, so s plus 3 gets cancelled, and 2 on s to be plugged in with minus 3 plus 1, it's a 2 upon minus 2, and so the final b value is minus 1. And so plugging in those values, a is 1 and b is minus 1. Remember this one, a is 1 and remember b is 1. And after that we're gonna have a standard Laplace transform, inverse Laplace transform pair, and that can be written directly, the inverse Laplace transform. So ha of s, that can be what is the value of a? It's a 1 upon s plus 1 plus b is minus 1 upon s plus 3. Alright, 3, or else it's a negative over here. So that is how h of takes the form when applying the partial fractions method, and then from there we can obtain the inverse Laplace transform to get ha of t. Alright, so and we don't need to do all that procedure. We have a standard relationship, how that S domain is converted into Z domain. So considering in general, so this is the transfer function, but more general transfer function of analog filter HA of S, which is equal to AI into 1 upon S minus PI, summation I equal to 1 to n. So what do we understand from this one? AI, it's a constant. Where do we have that over this equation? Guys, A was 1 and B was minus 1, isn't it? So with another pole location and number of poles, we may have b value, c value, something else other than this one, another constant. It's a constant. Ai is a constant over here. Can you see the similarity? 1 upon s minus p1, 1 upon s plus p1. This is the pole. I said this is the pole, isn't it? I said this is the pole. So here we have two poles. So this can be expanded as the summation can be expanded as a1 by s minus p1 plus a2 by s minus p2, or like that. And if we have so on, a3 upon s minus p3, the third pole, etc., etc. Writing that very equation in more general form. Okay, so this one, considering this transfer function, and so how to considering this transfer function, and we need to have that HA of t, isn't it? HA of t, and how that is obtained, guys, by applying inverse Laplace transform. For this one we will have HA of t, the inverse Laplace transform. We cannot apply Laplace transform, inverse Laplace transform for the summation, and this is a constant, this stands as it is. We're going to apply the inverse Laplace transform for this. Inverse Laplace transform for this, which I have just derived right now. So how can that be written? The inverse Laplace HA of t, HA of t is obtained by applying inverse Laplace transform for HA of s. Alright, so which is summation, nothing to do with that one, I equal to 1 to n, and ai is a constant, so we'll have inverse Laplace transform by s minus 1 by s minus pi. It's a pi, I equal to 1, I equal to 2, etc., etc. Alright, so just now we have did this, the inverse Laplace transform of 1 by inverse Laplace transform of 1 by s minus a will give us e raised to, if this is negative, we're going to have a positive t, u of t. We have to write the same thing for this one, inverse Laplace transform, which I have done right now. So summation I equal to 1 to n, ai is a constant, we don't touch it. So inverse Laplace transform for this one, it's a e raised to, it's a negative, so we're going to have a positive over here. In the place of a we have pi, that's it, minus a minus pi, so a will take that p over here, so it's a pi into t, u of t, more precisely ua of t, saying that it's of the analog signal. Alright, it's an analog signal which is HA of t, the impulse response of the analog filter. This is how we get it. Now we have to obtain the h of n. How to obtain h of n? When subjecting t equal to nt, which is specified t equal to 1, like that, subjecting t equal to nt, we will obtain that h of n from here. So h of n is obtained with h a analog of t, subjecting t equal to nt, plugging in t equal to nt. So h of n will be equal to h of n will be equal to this one, summation, no n factor over there, alright, no t factor over here, I equal to 1 to n as it is, and ai also as it is, and e raised to pi, and t is plugged in with nt, p n and t, u of nt, impulse response of the digital filter. And we have the impulse response of the digital filter, and how to obtain the transfer function of the digital filter. H of z is obtained by subjecting h of n to z transform. And what is z transform of h? What is z transform of any? What is that procedure? H of n, whatever we have, is multiplied with z raised to minus n and subjected to n equal to minus infinity to plus infinity, which is a both-sided signal, for a both-sided signal. But this signal, it's a causal signal, which is a right-sided signal, so the summation will be from 0 to infinity. And so h of z is given as the z transform, this one, alright, the z transform h of n. So we have this one summation. Watch carefully over here. This summation comes down as it is. This summation, which is n equal to 0 to infinity, multiplied, h of n is multiplied with z raised to minus n. Alright, z raised to minus n. We don't need this one, I need this place. What is a h of n? This entire equation, summation. What is h of n? I'm sorry, this is 1. I equal to 1 to n ai, that constant in the transfer function, ai into e raised to pi n into t, pi n into t, and this can be even simplified, guys. We can interchange the summation. All right, so interchange we are trying to evaluate for h of z, which is summation n equal to, so I equal to 1 to n, this summation. All right, we can interchange the summation, ai also as it is, and even this can be done in maths. Summation, interchanging the summation in the equation, n equal to 0 to infinity. This came out, this is e raised to pi into t, capital T, into z raised to minus 1 whole power n. And guys, this is a geometric series with infinite duration that can be written as h of z and I equal to 1 to n into ai as it is, into, guys, this can be it's very much the standard, n equal to 0 to infinity a raised to n. It's a geometric. If we expanding this one, what do we have? A raised to 0, that will be 1 plus a square plus a cube plus a4, a raised to 4, etc. to infinity. It's a geometric series with infinite duration, and this can be written as the answer for this one, 1 upon 1 minus a. 1 upon 1 minus a. So this can be, this one, the standard geometric series conversion. And this is, in this case, this a is that which is over, this entire thing is a. This entire thing is a. And so this takes off this form. How to write down this, including this summation, including this one, this summation, including this summation, this can be written like this: 1 upon 1 minus a. What is our a here? E raised to pi into t z raised to minus 1. All right. So guys, can you see some similarity between these two equations? The summation is same. ai and 1 upon s minus pi, 1 upon 1 minus this thing. So we start with this one. All right, we start with this one and we end with this one. This is how we convert. Let me tell that, considering this very numerical. All right, so this is the conversion equation for impulse invariant transformation, and making use of this equation, we don't need to do all these procedure, guys. We had this one. See, this one. This is very much this one. HA of S is this. Now we have to convert into H of Z, the digital filter which he asked for, t equal to 1. So how to write down this one? From this, with this very, this, can you see, H of S equal to 1 upon S plus 1. HA of S, this AI is 1 in that case. All right, so 1 minus 1 upon S minus pi equal to the same thing, 1 minus. And how that, from this H of S, how that H of Z is obtained? From this one, H of Z can be written as 1 upon 1 minus e raised to, guys, where is the pole? This is the pole. All right, this is the pole, this pi, 1 minus the pole. Where is the pole? It's at minus 1 into t as it is into z raised to minus 1. The next factor, minus of 1 upon 1 minus e raised to, where is the next pole? Once again the next pole, because we have the summation, we have the next pole, the second pole is at minus 3. In the sense, in the place of pi, we will plug in -3 into t into z raised to -1. This is the digital filter which we are in search of from this very equation. And what do we have? What did he ask for? That final digital filter h of z for t equal to 1. So this takes of the form 1 upon 1 minus e raised to, this t is 1, the sampling period is 1, so -1 z raised to -1 minus 1 upon 1 minus e raised to -3, t is 1, z raised to -1. Alright, so what value we have? 1 upon 1 minus, guys, e raised to -1, it's a 0 point, should be 3, 6, 7, 8, if I'm not wrong, z raised to -1 minus 1 upon 1 minus e raised to, and e raised to -3, e raised to -3, it should be e raised to -3 should be, if I'm not wrong, it's a 0.0497 value for e raised to -3, z raised to -1. This is for h of z. Cross multiplying this one, we will have that final digital filter which he is asking for. Alright, so cross multiplying h of z, that will be these two factors, 1 minus 0.367 into 3678 into z raised to -1 multiplied the denominator part, 1 minus 0.0497 z raised to -1, and cross multiplying this one, cross multiplying 1 minus 0.0497 into z raised to -1 is multiplied with I mean, okay, is that minus of this one, 1 minus 0.3678 z raised to -1. Alright, so solving this one, solving this, what do we have? Solving this, we have 1 minus 0.0497 z raised to -1 with this. Alright, 1 minus, and minus 0.3678 z raised to -1, and plus what do we have? That it's a what is that? What factor do we have? 0.3678 into 0.0497, isn't it? 0.97, which is 0.0182 z raised to -2, and multiplying, I mean this one, 1 minus 0.0497 z inverse -1 minus into minus plus 0.3678 z raised to -1, and plus 1 minus 1 will be cancelled. What do we have? 0.3678 minus 0.0497, that will give us 0.3181 z raised to -1 upon 1 minus 0. Guys, it's 0.0497 plus 0.3678. This will be 0 minus 0.4175 z raised to -1 plus 0.0187 z raised to -2, and this is the required digital filter. That's it.